Now, we will discuss few numerical design problems related to cache memory that will help you in solving the exercises. So, consider this question where for a 32 KB direct mapped cache with 128 byte cache block, give the address of the starting byte of the first word in the block that contains the following address. So, in what way we could, so processor is giving an address like this. This is the address given by processor and the specifications of cache memory is given. We wanted to know whenever this particular address is given, a block of data is going to be identified. What is the address of the starting byte of the first word that contains this particular address? So, the first thing that we have to do here is we have to find out what is the split up of the address. So, the number of sets that we need is defined by cache size by block size into the associativity. Here the associativity is 1, we are using a direct mapped cache. The cache size is 32 KB. 32 KB means it is 2 power 15. 32 is 2 power 5 and k is 2 power 10 and block size is 128 bytes. So, once you have 128 bytes, it is 2 power 7. The associativity is 1, that is a direct mapped cache. This will effectively give you 2 power 8. So, in the address split up, we have 8 bits that is going for the sets and the block size is 7 bits and the remaining is basically your tag. Since the number of bits in the address is not given in the question, the tag bits is not relevant here. 8 bits are used for indexing, this is what is called the index bits, and the last 7 bit is called the offset. Now, the question is what is the address of the starting byte of the word? So, this is the address that is given A23847EF. So, you have 8 plus 7 15 bits. So, this will basically go into your tag. The last 15 bits. So, 8 plus 7 15 bits are there. This is what is needed. Now, these are the last 8 bits E and F. So, E stands for, when you write it in binary, this is E and F stands for 1111. These are the last 8 bits, out of which the last 7 bits will tell you what is the byte number within that block. Now, all the other 25 bits of the address, for example, you assume it is a 32 bit address, last 7 bit is your offset. When you put the last 7 bits as fully 0, that is the first byte of this block, and when the last 7 bits is fully 1, it is the last byte within this block. So, effectively the address of the first byte is going to be, by making the offset bits completely 0. So, if you wanted to make it completely 0, then it becomes 1 0 0, there are only 7 bits, 0 0 0 0, that the value is going to be 80. So, this is the answer that we need. So, whenever we get a cache block, when you fit the last n bits, where n is the number of bits required for offset, when those n bits are put to 0, you get the very first byte, and when those n bits are put to 1, we will get the last byte. So, this is the answer for this problem. Moving on to the next problem, a cache has 256 KB capacity with 1 byte word. So, one word is 8 bits. It is using 128 byte blocks. It is 4-way associative. System is using 32 bit address. So, the physical address is 32. You have 2 power 32 locations in your main memory. Given the following addresses, which set of cache will be searched, and specify which byte of the selected cache block will be forwarded if it is a hit in the cache. So, the question is, you have given the specifications of cache memory. Now, an address is given. From the address, they will find out what is the index to be searched. So, go to that corresponding index and then perform a tag comparison. If it is a hit, you have to return one particular word. Here one word is 1 byte. So, the question is which is the set that is searched, and if it is a hit, then which is the byte that is returned. Let us first work into the split up of the address. So, number of sets can be defined as cat size by block size into associativity. Cat size is 256 KB and that tell you 2 power 18 bytes, and block size is 128 bytes, so it is 2 power 7. The associativity is 4 because it is 4-way associative, it is 2 power 2, then it is 2 power 9. This means I have 512 sets. The split up of the address is going to be total of 32 bits are there, out of which the offset is 128 bytes. So, 7 bits are used for offset. Since I have 2 power 9 sets, 9 bit is used for the indexing. So, 9 plus 7 is totally 16. So, the remaining one, so altogether this is going to make this. So, this is your index bit and this is the offset bit. Now, what we have here is from the given address, this is the address that is given. From the given address, we have to find out which of the set index will be searched, and after searching that particular set index, if it is a hit, then which of the word that is going to be extracted. So, our problem now is we have a 16-bit tag, a 9-bit index and a 7-bit offset. The address given is ABC89987. We know that it is a 16-bit tag. This is a hexadecimal address. So, these 4 is going for the tag. That is not relevant for this current problem. Let us now consider 9987. These are the hexadecimal notation for the last 16 bits. So, 9 stands for 1001, next 9 stands for 10001, and so this we have 1 here. So, 9987, 8 is 1000 and 7 is 0111. So, this is the split up 9, 9, 8 and 7. Out of which the first 9 bits is going to be the index bits. So, this much is the index bits, first 9 bits, the last 7 bit is offset. When you compute the binary to decimal conversion, the value that you get is 307 and this value is 7 because it is. So, in short, out of 512 sets which ranges from 0 to 511, that is the numbering that is given, for this given address, the cache controller is going to search in 307th set. Since it is 4-way associative, you will search in all the 4 blocks of set 307 and see whether the tag that is stored is ABC8, it is a 16-bit tag. If it is a hit, then in that particular block, extract the 7th byte or the 7th word. In this case, 1 byte and 1 word is same. So, given an address, this is the way by which the cache controller will come to know whether you are going to search in nth set. So, in this problem, 307th set will be searched. Moving on to the third problem, it takes 2.5 nanosecond to access the tag and 4 nanosecond to access data array and 1 nanosecond to perform hit or miss comparison and 1 nanosecond to return the word. What is the cache hit latency of the system? We will try to solve the first section. Once given an address, CPU is giving an address, there are 2 things that happen. One is tag array you are going to access, and then you are going to have a data array. Now, once you get into tag array, because once you do the indexing, you will find what is the tag value that is stored there and what is the data value that is stored there. Once you get the tag array, then you are going to have a hit or a miss comparison. Hit or miss comparison is there, and then you return the data. So, it is a question that is given like this. Now, we will try to understand in this problem the tag array access is going to take 2.5 nanosecond and data array access is going to take 4 nanoseconds. It takes 1 nanosecond to perform hit or miss comparison. We have to understand that hit or miss comparison is basically from the incoming address find out what is a tag value and compare it with the tag value of the selected index. So, already in 2.5 nanosecond tag array is accessed, you have retrieved the tag value there. So, you spend another 1 nanosecond here and 1 nanosecond to return that. So, it is like two parallel activity. One activity is accessing tag array followed by comparison of the tag value and second channel is taking done. So, the access time depends on out of these two branches which branch is taking more time. The left side branch, that is tag array and hit or miss comparison, is taking 2.5 plus 1, that is 3 nanosecond, and the right side accessing of the data array will take 4 nanosecond. So, the maximum of these two, that is 3.5 or 4 plus the time required to return the data. So, this 3.5 is basically for tag and this 4 is basically for data. In this case, the data is dominating. So, it is basically 4 plus 1, 5 nanosecond is the cache hit latency. So, the A part of the question is what is the cache hit latency? It is going to be 5 nanosecond. Now, the B part of the question, what would be the hit latency of the system if both tag array and data array take 2.5 nanosecond and hit or miss comparison will take 1 nanosecond. So, in this case, we will try to rework that whatever is given. So, still the accessing pattern is still the same. There are two parallel units that is there and we are going to rework on these values and these values are to be reworked. Now, for this question, it takes 2.5 nanosecond for both the tag array and the data array. So, both will take 2 nanosecond and 1 nanosecond for hit or miss comparison. So, what is and all other parameters same. So, in this case maximum of this is 3.5 or 2.5, this is for tag and this is for data plus 1. So, it will be 3.5 is maximum plus 1. So, the answer is 4.5 nanosecond. So, we have to understand that accessing of tag array and accessing of data array happens parallelly and whichever side is dominating, that is the maximum delay that is being encountered, plus once these two branches merge together and then we have the time for returning the data. Moving on to the next problem, this is basically to find out miss penalty. A cache has a hit rate of 95%, 128 byte block, and the cache hit latency, that is called hit time, it is 5 nanosecond. Main memory takes 100 nanosecond to return the first word. Here first word is 32 bits of a block and 10 nanosecond for each subsequent word. What is the miss latency of the cache? We have seen that the average memory access time is defined as hit time plus miss rate into miss penalty. We have the values of hit time. Let us try to consolidate the values. Hit time is 5 nanosecond and miss rate is 0.05 because the hit rate is 95. So, miss rate is going to be 0.05, 1 minus hit rate. Miss penalty is not given to us. So, how will you get miss penalty? What is miss penalty? The time that is taken to transfer a block from the next level of memory. In this case, it is main memory. From main memory, you have to transfer a one block. But this block cannot be transferred in one stretch. The problem says that it takes 100 nanosecond to return the first word. Multiple words constitute a block. It takes 100 nanosecond to return the first word because you have to index into the cache memory, locate the data and then transfer. That is why it is taking a bit more time for retrieving the first word. And each subsequent words will be returned in 10 nanoseconds. So, first we have to see how many words are there. See, number of words per block. So, each block is 128 byte and one word is given as 32 bits, 32 bit is 4 byte. So, you have 32 words are there. The first word will be returned in 100 nanosecond. So, you have another 31 more words, they will take only 10 nanosecond each, making the value as 410. So, the miss penalty is 410. If the question is all about average memory access time, which is not asked in this question, if the question would have been average memory access time, hit time is 5 nanosecond plus miss rate is 0.05 and the miss penalty is 410. Once you solve this, you will get average memory access time. And what is a cache miss latency? It is 410 nanoseconds. So, that completes problem number 4. Now, we will take up the last problem for the day. This is a problem where you are given a multi-level cache. You have an L1 cache and an L2 cache. When you have an L1 and L2 cache and its specifications is given, the question is average memory access time of the entire memory hierarchy. So, average memory access time, like what I have mentioned previously, it is defined as hit time of L1 plus miss rate of L1 into miss penalty of L1. This miss penalty of L1 can be defined as hit time of L2 plus miss rate of L2 into miss penalty of L2. So, let us try to compute these values. What is hit time of L1? L1 hit time is 1 cycle. So, it is 1 plus L1 miss rate is 2.5. So, it is 0.025 into then the miss penalty of L1, that is not directly given, we have to compute. It depends on hit time of L2. So, L2 hit time is going to be 6 cycles, 6 plus miss rate of L2, that is 10%. So, it is 0.1 into miss penalty, that is 120. So, this is the hit time of L2, miss rate of L2 and miss penalty of L2. This much time is the miss penalty of L1. So, once you solve this, you will get the answer of average memory access time. So, few more tutorial problems are already there, which is uploaded in the site. You just work with few more problems. This will give you, working with these kind of problems will give you more clarity on how cache memory works. So, with this we end the tutorial session. If there is any doubt regarding solving of any of these questions, feel free to post your queries or mail us. Thank you.